Everywhere we look, water pollution threatens communities. Dirty water spreads disease, ruins crops, and destroys ecosystems. As an environmental sanitary engineer, I study how we can purify and restore water. There are many ways: filtration, coagulation, distillation, and even electrocoagulation, and today, we'll demonstrate them step by step. To make this journey fun, let's bring in our two friends, Curious and Smart. Curious asks the questions you might be wondering, and Smart explains the science behind them. Let's begin.
So what's our first method of water purification?
We'll start with sand filtration, one of the simplest and oldest purification methods. We place filter paper in a funnel, added fine sand followed by coarse sand, and pour dirty water through it. The sand layers trap dirt, debris, and solid particles as water passes through.
Oh, just like how soil filters rainwater naturally, and I could totally see that the dirty water is much clearer now. But I'm just a little bit curious, what type of mixture is clay and water?
That's a suspension. Clay doesn't dissolve, but floats or settles over time.
So is any clay present in the filtrate?
No, clay particles are too large to pass through fine sand and filter paper, so the filter is clearer.
And lastly, could this remove salt?
Sadly, no. Sand filtration removes solids but not dissolved chemicals like salt or chemicals.
So that means that this method is just great for visible dirt, but not for desalination.
Exactly. It's often the first step in water treatment.
Now that we've removed large particles, let's see how we handle the tiny ones that won't settle or filter easily.
So what's the next method?
Next is sedimentation and coagulations, which helps remove suspended particles too small to settle naturally. We filled two test tubes, one with sand and water, and the other one with clay and water, and shook them well. The sand settled quickly because it's heavy. The clay stayed cloudy because its particles are too small to settle.
Now let's see how coagulation helps.
We divided the clay mixture into two tubes. Tube A, just clay and water, and Tube B, add 5 drops of aluminum sulfate and lime water. After a few minutes, Tube B cleared up. Flux formed and settled to the bottom. Aluminum sulfate and lime water form aluminum hydroxide, a sticky substance that traps clay particles.
So that's why it cleared up. But what about the other mixtures? We also tried water with only aluminum sulfate and lime water. So it just stayed clear because there were no impurities to bind to, right?
Exactly. The reaction only helps if suspended particles are present.
So what type of mixture do the tubes represent?
Both are suspensions, but in the treated tube, coagulation binds particles so they settle.
After standing, what happened to the sand? And what happened to the clay?
Sand settles quickly by sedimentation. Clay stays suspended unless coagulated.
So what is this purification process called?
This is coagulation and flocculation, followed by sedimentation.
So what happens when the aluminum sulfate and lime water mix?
You undergo a double displacement reaction.
So what happens in the clay with aluminum sulfate and lime water mixture compared to the plain clay water only?
The clay settles faster and water clears up because flocks drag down particles.
So what causes the solution to clear up?
Formation. Aluminum hydroxide acts like a magnet that binds fine particles.
So what process is this? And as far as I know, this is also represented by the letter C.
Chemical coagulation, key in water treatment plants.
Can this now remove salt?
No, only suspended solids, not dissolved salts.
So this type of purification of water is just best for muddy or turbid water.
Now that we've learned how to clear cloudy water, let's move on to removing dissolved substances using heat.
So what's the next method?
Distillation. It separates substances based on boiling points. Here's our setup. We have distilling flasks to heat the solution, condensers to cool vapor, receiving flasks to collect distilled water, and thermometer and heat source to monitor temperature. We dissolve red dye and 0.4 grams of sodium chloride in 15 to 50 ml of water, poured it into the flask, and heated it until it boiled. The water vapor rose, leaving behind salt and dye. They condensed into clear liquid. The distillate was colorless while the original remained red. We measured the conductivity using a multimeter. The the original had high conductivity because of the salt, and the distillate had low conductivity, showing that most dissolved solids were removed.
So does distillation remove dissolved solids?
Yes, it removes both solids and salt, since only pure water vapor condenses.
Well, can you explain your answers further?
Heating evaporates only water. Impurities with higher boiling points stay behind.
So this method of purification is best for obtaining fresh water from seawater, right?
Exactly. That's desalination.
Now that we've purified water through heat, let's see how electricity helps treat colored wastewater.
Ooh, this one looks really polluted. So what's the next process, Smart?
This is where we try to remove color by electrocoagulation, a process that uses electricity to help clean the water.
By using electricity? Well, that's interesting. Can you show me how it works, Smart?
Let's set it up. We inserted two iron paper clips on opposite sides of a 50 ml beaker, then connected a 9-volt battery using alligator clips. Our wastewater was dyed blue, so we set aside 1 ml as a reference and poured 25 ml into the beaker.
And then you turn the power on.
Exactly. Once powered, the anode began dissolving, releasing iron ions while the cathode produced hydrogen bubbles. As the reaction continued, the blue water slowly turned greenish, and the rust-colored sludge formed the pins. The rust is actually iron hydroxide, and it works like a sticky magnet that traps the dye molecules and other impurities.
So the color change means that it's working.
Yes, after about 10 to 20 minutes, most of the color disappeared. Then, we filtered the treated water again through sand. The filtrate was much clearer.
So now that it's working, can we drink it right away?
Not yet. Electrocoagulation removes the color and suspended solids, but some dissolved chemicals or bacteria may still remain. It's best used as pre-treatment before the final disinfection.
So that makes me wonder, how come a well drilled into the ground produces clear water?
Great question. The ground acts like a natural filter. As water seeps through sand, gravel, and rock layers, suspended solids get trapped, leaving the water clearer, similar to how filtration works in our experiment.
So speaking of filtration, what types of impurities can be removed by using the different methods?
Let's break it down. Filtration removes solids like sand or clay. Coagulation removes fine colloids that don't settle easily. Sedimentation removes heavier particles like grit or large sand. Distillation removes dissolved solids and salts by turning water into vapor and condensing it back.
Then what kinds of impurities can't be removed by those methods?
Good follow-up. Chemical contaminants, dissolved gases, and some microorganisms can slip through. That's why no single method is perfect. We often combine them for full purification.
So electrocoagulation sounds like a modern technique. How does it exactly work again?
In electrocoagulation, electric current passes through metal electrodes, like our iron pins. They release iron ions that react to form iron hydroxide, like the rust we saw. The hydroxide clumps together with dyes and impurities, forming flocks that settle or can be filtered out later.
Oh, so that explains why the blue water turned into green and rust formed from the safety pins, right?
Exactly. The color change can mean that reaction is actually happening. Afterward, filtering the treated water helps it make it better. Though for drinking, we'd still need further disinfection to kill the bacteria.
So now, we have already seen filtration, sedimentation, coagulation, distillation, and electrocoagulation, each with its own role in water purification.
Right. Together, they show how science can transform dirty water into something much cleaner.
And I hope you all learned a lot about how water purification really works, from natural filters to modern coagulation.
Remember, clean water is life, and every drop counts. Thanks for watching. Stay curious, stay smart, and protect our water.